Buenos dias. I've just exhausted my Spanish on you, so but I look forward to providing you some, I think, important information that will hopefully allow you to make some good, sound decisions based on the science as we know it. So what we want to talk about here, and it's going to build on the previous talk here a little bit, is water quality associated with hydraulic fracturing in shale formations. And one of the most critical aspects of developing any kind of resource, whether it's fuels or perhaps quarrying rock, and anything that we're getting into the earth for, we need to establish the baseline conditions so we understand what the water quality was before the activity and can understand if the activity had any impact and be able to sample post mining or drilling samples. So initially, I'd like to just describe what the fracturing fluid characteristics ought to have in them. For one, you want to use a fracturing fluid that is non-damaging to the shale. And by that we mean we don't want to have the fracturing fluid potentially impact the production of the hydrocarbon from the shale. So you want to have it to be non-damaging. You don't want to form skins or other scales that could potentially impede the flow of the hydrocarbon out of the shale reservoir and into the well. We need to be careful about making sure that scale is not going to be an issue. Oftentimes that's controlled by pre-treating the water that's being injected down into the reservoir, or it might be chemically controlled by additives that prevent iron or other scale-forming agents down there. Obviously, you need to be able to open up fractures in these highly impermeable formations. And so you need to be able to get the proppant out into the fractures to be able to hold open the shale, to be able to allow, again, the hydrocarbons to be liberated from the formation. In areas where, such as Pennsylvania, where there's a high percentage of reuse of the fracturing wastewaters or the produced fluids, one of the major innovations to allow that reuse is the fact that brine or salt-tolerant friction reducers have been developed over the last few years. Many times you can have the chlorides that naturally occur down in the shales interfere with the friction reducers that really, one of the reasons why slick water hydraulic fracturing works so well. And if you have an adverse interaction there, you won't have as effective a fracturing treatment. And so being able to overcome the chloride interaction by using brine-tolerant friction reducers allows the fracturing to be more effective while also being able to reuse more of the produced fluids. In general, you want to be able to have the fluids you inject down into the shale be recovered so that basically the hydrocarbons can flow out of, again, the shale and into the wellbore better. We're starting to see some companies actually shut the wells in for longer periods to allow the shale to relax and then recover the fluids back out of there. So we're trying to see what techniques work better to actually, again, release those hydrocarbons. Really the name of the game here is developing, at the end of the day, a very effective and extensive fracture network. And the more surface area you create down in the shale, the more, in general, hydrocarbons you're going to be able to develop, and the more effective or the higher your recovery efficiency will be. All of this obviously needs to be, cost effective. There are, as you saw in David's presentation earlier, the cost of developing these shales can be quite variable depending on where in the world you are. And so obviously the cost of the fracturing needs to be highly considered. There are some other options out there, not just water, but in some cases we're seeing liquefied propane gels be used. There are some potential advantages, but there are some potential drawbacks. One of the major drawbacks would be the availability of large volumes of propane on site, transporting that propane, and then there are cost factors there. But one of the potential advantages there is putting a hydrocarbon into a hydrocarbon reservoir means that fracturing fluid, or that carrier fluid, is going to be much more compatible with the shale, and therefore you might have less damage to the shale, and you might ultimately have higher recovery efficiencies. And in many of our conventional formations, fluids such as supercritical carbon dioxide or nitrogen foam fracking techniques have been used. Some companies are looking at just how viable these conventional fracturing fluids might work in an unconventional formation, and probably might be more effective where you have a shallower reservoir where the pressures aren't as high. And that tends to be one of the major limiting capacities of these alternative fracturing fluids is, the pressure limitations. You can only build up so much pressure with propane or nitrogen or carbon dioxide. And that's what makes water so effective, is because it's virtually incompressible. So the pressure you impart on the water at the surface translates very well down into the shale itself. Just want to touch on the fact that now in Pennsylvania and several other states in the U.S., it is now required that the fracturing fluid mixture be publicly disclosed on fracfocus.org. And so I wanted to bring up the fact that that was one of the most controversial aspects of shale energy development was what goes into the secret recipe. Now anybody can go onto this site and look at many of the wells that are being drilled. Some companies are doing this voluntarily, while others, again, it's now a law. And so you would see a Google Earth image like this. You can click on one of the blue drops there, and then you would get a page that shows for that particular well just exactly what went into the mixture. And it gives quite detailed information on the percentage of the additive by mass. It gives you the chemical abstracting number, so you can actually look more in depth as to what might be the toxicology of that particular compound. What are the material safety data sheets tell us? So this is all very useful information when considering perhaps just how hazardous these compounds might be. And I blew this up. I know this is probably very, very difficult to read, but I hope you'll all be able to see it when you get the presentations. But you can see there's quite a wide array of chemical additives. In some cases it might be just a handful of chemicals. In other cases it might be upwards of 20 or more compounds that have very difficult to pronounce names, so I won't make the translators suffer through that right now. But again, some of these compounds definitely would be hazardous if they were to get into drinking water or otherwise ingested. And so obviously that's one of the things we need to be very careful about, is how these fluids are managed at the well sites, to make sure they aren't released into the environment, to make sure that the shale reservoir that they're being injected into is hydraulically isolated from any underground drinking water sources or surface waters for that matter. And that was the Marcellus example. Different shale reservoirs are going to have different fracturing additives. This is an example from the Bakken Shale up in North Dakota and Montana, where it's not so much a gas shale, but rather more of an oil shale. And this is really kind of transforming North Dakota into being one of the leading oil-producing states in the United States. And again, the mixture is going to be a little different, and each company has a different philosophy on what chemical additives work best for them. Obviously, there are different service providers out there, whether it's say a Halliburton or a Schlumberger or a Baker Hughes. Each of those companies obviously have their own mixture, some of which might be proprietary. So there might be maybe out of the 20 additives, maybe there's 2 or 3 that they don't have to disclose because of that trade secret. So it would be therefore considered proprietary, and that's what gives that particular company a perceived advantage over the other companies that do fracturing in these wells. But I just want to make it be known that on fracfocus.org, again, you can look up very specific information on what these fracturing mixtures consist of. So it's there's a lot of controversy about what goes into the fracturing mixture, but not quite as much controversy as to, well, what naturally occurs in the earth and what's coming back out. And in many cases, the naturally occurring elements that occur in these shales come out in relatively high concentrations that would probably be, in many cases, more toxic than any of the additives you put into the fracturing mixture, because ultimately that fracturing mixture, the additives are pretty dilute, but you can get relatively high concentrations in the produced fluids, the waters that come back out of these wells after hydraulic fracturing has taken place. And some of the more common contaminants or constituents of concern here would include the total dissolved solids, which kind of measures everything that's dissolved in the fluids. We're talking about primarily salts, sodium chloride, for instance. And chloride tends to be about 50% of the makeup of the total dissolved solids concentration. So if you were to take a water with a high total dissolved solids concentration and release it into the environment without any sort of treatment, and it would get into a freshwater stream, it would have severe impacts on the freshwater species in that stream because they're not saltwater species. There can be some volatile organic compounds, or VOCs. Some of those may actually be added into the fracturing fluid mixture, but some of those may also be naturally occurring come out of the shale formation itself. Ultimately, whatever the source is, they can be in these produced waters, and therefore you need to be able to measure what are the concentrations of these volatile organics, and can they be treated? Yes. What do you do with the water to make sure they don't get into the environment? And some of them can be, pretty nasty. The BTEX here stands for benzene. We're all probably heard of benzene. It's a contaminant that's commonly associated with, say, gasoline or other fuels. Again, it's a naturally occurring hydrocarbon, but it doesn't mean that it's not toxic to us. Toluene would be the T, ethylbenzene would be the E, and the X would be xylenes. Again, these are all naturally occurring down in hydrocarbon reservoirs, whether it's conventional reservoirs or shale reservoirs. But we need to make sure that we understand the concentrations and whether there's any sort of potential for exposure to humans or for release into the environment. Radium-226 is a naturally occurring radioactive material, or a norm for short, that occurs in these shale reservoirs. When the shales are originally deposited, you get uranium and thorium are part of the shale, and as they break down, you get decay products like radium-226 or radium-228, which in high enough concentrations, obviously, again, could have an impact on human health if it were to somehow end up in drinking water. The problem with radium is it does a very good job of sort of mimicking itself as calcium, so it can get into our bones, and so that's what actually makes it fairly potentially toxic. Barium and strontium are two of the more common metals that are associated with these shale reservoirs, and again, they end up in the produced fluids. And they're often actually sort of the focus species for treatment for recycling purposes. Reason being is if you were to recycle these produced fluids for reuse in hydraulic fracturing, the barium and strontium can be potential scaling agents. That is, they could potentially precipitate down in the shale and plug up the fractures. So many companies try to specifically treat for these compounds. And when they treat for these compounds, actually the radium tends to precipitate out along with that in the sludge. But now you've got a sludge to deal with. So what we're seeing is, in total, the toxicity of that sludge is it's relatively insoluble, and the radiation emissions are low enough that, at least in Pennsylvania, it's not considered to be generally hazardous, and therefore can be disposed of in a residual waste or municipal landfill where permissions are granted. But there does have to be screening and testing of these sludges to make sure that there isn't going to be a subsequent release of those constituents back into the environment. This just shows what the produced fluid water quality looks like over time. So the blue line would represent that total dissolved solids concentration. The red line would show what volume of produced fluids you get with time. In general, you get an initial higher volume of the fluids out of the well. That's commonly known as flowback. And then once the well is put online and producing gas, becomes produced waters. But basically, it's all water that came out of the shale. But the critical thing to know here is that as time goes on and the longer that water's been down there in the shale, the higher the total dissolved solids concentration gets, because it's had time to mix with the fluids down there or dissolve out some of these contaminants out of the shale. And so you're going to see the salt concentrations increase. You're going to see the barium and strontium concentrations generally increase, as well as the radionuclides. But the good news is you get lesser and lesser of that water as time goes on. That was the Marcellus example. This just shows some of the other major basins in the United States, and just shows you the range of the total dissolved solids concentrations, and it can be quite variable. For reference, the oceans generally have a TDS concentration of about 35,000 parts per million, and some of these basins might have a produced water TDS concentration of maybe just 10,000 to 20,000 parts per million of TDS. And then some, such as the Bakken and the Marcellus, you get upwards of 200,000, 300,000 parts per million with respect to total dissolved solids. And so that can represent some challenges when treating and or reusing this water, because the higher the total dissolved solids concentration gets, the more difficult and the more expensive and the more energy intensive it becomes to manage and treat these fluids. Again, I'd mentioned that it's not only the salt concentrations that increase, but also things like barium, strontium, and iron increase. So those, again, are potential scaling agents. So in general, when companies are hydraulically fracturing a shale, they don't want to have high concentrations of these cations, these metals, in the water. So oftentimes they will treat by special treatment technologies. Oftentimes it's chemical precipitation to drop out these metals. But as the metals concentrations increase, it's going to be, you're going to need more chemicals to precipitate out these cations. But it's a fairly conventional treatment technology that's been out there for other industrial uses for decades. This is actually a study that just came out just about a month ago by some researchers at Penn State. And what they were doing is trying to determine what the origin of the salts and other contaminants in the shale is. Is it from a formation deeper? Is it from inherently in the shale itself? And that's kind of an interesting research topic in our area. But I thought it was just interesting that they did show a very positive correlation between the barium concentrations and the radium concentration. So in general, where you have one, you tend to have the other. Again, it's one of the most critical aspects of all this is being able to establish what the pre-drilling baseline conditions, water quality conditions are in any area. And I would venture to say in some areas where there's active shale drilling going on, the sampling of water before drilling was more of an afterthought. And so the drilling may have gotten out ahead of the water quality testing. But we are seeing an incredible amount of water sampling going on, especially in Pennsylvania and other states, to establish those pre-drilling water quality conditions. But because, again, if we don't know what the water quality was before drilling and we suspect that there may have been some sort of contamination event related to drilling, we don't have anything to look back at for comparison. So we really need that pre-drilling and post-drilling so we can do a before and after comparison. And why that's important is because there are naturally occurring elevated levels of what we would consider to be contaminants that are already in these aquifers. They've been there for millions of years. It has nothing to do with drilling. It's just that there are naturally occurring contaminants out there. And we're all familiar with arsenic. And this is a study done by the United States Geological Survey about 5 years ago up in northern Pennsylvania. And they did, in fact, find elevated levels of arsenic in private drinking water wells that's naturally occurring. And probably one of the more infamous cases of did drilling impact water up in Dimock, Pennsylvania, where this study was basically done. Yeah, they did find some elevated levels of arsenic in the private wells where that drilling was occurring. But in many cases, there might not have been pre-drilling surveys to say whether that was related to drilling or if it was there in the first place. But if you look at this study, it was done before 2007, published in 2007. It shows that many areas did have elevated arsenic well before any drilling was occurring in there. Gas happens. You can have methane in groundwater, naturally occurring, very unrelated to drilling. This is an actual natural gas seep in the Eternal Flame Falls up in New York State, where the Marcellus and other black organic rich shales come up to very close to the ground surface. And so there's not a lot of methane there. But there's enough that it will show up in drinking water wells, and you can actually have these naturally occurring seeps. And I guess some brave soul goes up here every once in a while and lights this on fire because it makes for a pretty cool picture. And this was a study that just came out by the collaboration between the New York State Geological Survey and the United States Geological Survey, and they did methane in groundwater sampling, and did find that about 53% of the wells in that study area had detectable methane in areas where there wasn't drilling. So again, that's why it's really critical to collect these samples. As you can tell, I'm very much stressing how important that fact is. Because there, again, are multiple sources of methane. You can have microbes breaking down organic material in near-surface soils, producing what we would call biogenic methane. You can have coal bed methane. You could have methane emanating from a landfill. Or you could have a leaking oil or gas well. It could be a well that might have been drilled decades ago and wasn't drilled to today's standards and allows hydrocarbons to leak up. It could be a more modern well that just didn't have adequate construction to seal off the hydrocarbons and could allow methane to leak up. And that has unfortunately occurred in a relatively limited number of cases, but is a threat. And I think, as John Hanger will explain later on today, our regulations have evolved in Pennsylvania to address some of these issues as they do arise. Again, this is that study from New York, and it just shows that, in fact, many of these wells that were sampled from around the state did have elevated levels of methane in groundwater. And a lot of that has to do with what formation you're collecting those samples from. Many of the what we would call the Upper Devonian shales, they have hydrocarbon potential, but they're also used for aquifers for drinking water. And so you would kind of expect that you would find some concentrations of methane in these relatively shallow gas-bearing formations. And this just shows the distribution of the concentration of methane in these wells from this New York State study. So you can see a relatively small number of the samples had a concentration of greater than 28 milligrams per liter, which is the saturation index or maximum saturation that you would expect to find of methane in groundwater. Beyond 28 milligrams per liter, it would effervesce out of the water. But a relatively high number, 7% had concentrations between 10 to 28 milligrams per liter. About 8% were 1 to 10%. And then 36% of the samples were less than 1 part per million, but still there's a detectable amount of methane in that groundwater. So you could say that that's relatively common to have a very, very low concentration. And it's kind of rare to have anything at 28 milligrams per liter or higher. Just another example, just to the south of Pennsylvania is West Virginia, which has seen a lot of historic drilling and coal mining over time. And again, they're finding that they in fact have methane in a high percentage of their wells, but it also is very geographically dependent. It's south of this geologic hinge line, as they call it here, is where you get the highest concentration of methane in groundwater. And some of this, could be depending on when the samples were taken and how close they are to drilling. Some of it could be legacy issues from wells that may have been drilled decades ago. They didn't really go out and try to spell that out in the study, but that is a real issue. Just to give you a sense of the potential magnitude of that issue is in Pennsylvania. We had the first oil well in North America was drilled in Pennsylvania in Titusville in 1859. They hit oil at 69.5 feet below the ground surface. So at 20 meters, they hit oil. Since then, we've had on the order of 350,000 oil and gas wells drilled in Pennsylvania. And we probably don't know where 200,000 of those wells are. They were never abandoned with today's more modern standards. And so you could very easily have oil and or gas migrating up along these old wells that were never properly abandoned, sealed, plugged. And so we very well do have some legacy issues in Pennsylvania, and that's why, based on what we now know, we know how to do this a lot better. The technology's improved, the regulations improved, and we hope that going forward here, you can learn from some of those lessons that we've dealt with. This is another study that was done by our United States Geological Survey. And what it looked at was the fact that some residents up in northern Pennsylvania had complaints of what they thought was maybe methane in their groundwater wells. So the USGS, along with some folks at the Department of Environmental Protection, our state regulatory agency, took a closer look at this situation and did some sampling and found that many of the wells in the area, as denoted by the red circles here, had biogenic methane in the groundwater. That is, methane that's generated from microbes. And so you can see it's kind of spread around in a sort of even distribution, random distribution there. But there are some gas storage fields up in this area. Basically, we've got relatively deep sandstone reservoirs that we inject natural gas into when our demand's lower, and we pull that gas back out of that storage when the demand goes up, especially during the winter when we enter our heating period. And so that's how we kind of buffer our supply and demand, is by the use of these deep gas storage fields in these relatively permeable sandstones. Well, it appeared that somehow, perhaps one of these reservoirs may have leaked. It might have been just along a natural fault. geologically, or it may have been along one of the injection wells or one of the monitoring wells. It's not really clear where the breach was in the system, but they knew that they did have some methane in some of these wells. So they went back, they found an even distribution of biogenic methane, and then when they went and sampled some other wells, they found that in a fairly tight cluster was thermogenic methane that came from deeper in the earth. And if you note that it's pretty much along a anticlinal structure, an upward fold in the rock, which is often tapped as a conventional reservoir feature, because oftentimes you have gas trapped in the top of that arch. And then you have a major river coming down through here. Rivers tend to follow zones of enhanced fracturing. And so it would appear here that you have near the intersection of a zone of enhanced fracturing with a geologic anticline, you had a cluster of thermogenic methane. And so based on some isotopic testing of that methane, they did find that in fact it probably did come somehow from these gas storage fields. So again, just goes to show the power of testing water quality, whether you're trying to establish baseline conditions or do some forensics to figure out what is the source of methane or any other contaminant in groundwater. And this is the results of their study. So what they showed was most of the samples they collected fell within the thermogenic regime. And so what you're looking at is the carbon-13 isotopes relative to the hydrogen isotopes. And so they have a pretty well-defined area in which the thermogenic methane would plot. It has a pretty well-defined carbon and hydrogen isotope composition. And then you can see over here you get more of the biogenic methane, which tends to be lighter with respect to the carbon isotope. Just want to mention that some researchers at Penn State did a state-funded study to look at water quality before and after Marcellus drilling. So they went in and collected pre-drilling surveys, water quality survey data, and then went back in after the wells were drilled and or fractured and collected data. They sampled a total of 230 wells, and they didn't find that there was really any significant impact on the groundwater quality as a result of drilling. But what they did find is that about 40% of the wells failed for at least one drinking water standard, probably something like coliform bacteria, maybe nitrates. And then about 24% of the wells had some detectable methane in groundwater. Again, this is before any drilling occurred. So again, stressing the importance of setting the baseline conditions here. And this is one of the tables from that same study. And what they're showing is the sort of the median concentration of groundwater quality in Pennsylvania as we know it, the median concentration of the Marcellus wastewaters, and there's some significant differences. And so that would allow you to figure out whether there was some sort of a release from Marcellus drilling operations into groundwater. And those critical parameters would be, again, the total dissolved solids. It's almost 70,000 parts per million on average, where it's only 163 in groundwater. So you would see, if there were some release, you would see that in the groundwater. Again, barium is another indicator parameter. Strontium is another strong indicator parameter. So there are some pretty some basic chemistry that you can do to evaluate whether your water quality may have been impacted by any sort of shale gas drilling operation. And this is sort of that one of the major plots from this study is the total dissolved solids concentration before and after drilling. And it's pretty much a straight line. There's a couple of stray points, but for all intents and purposes, there was really no impact before or after drilling. So just some thoughts on some of the critical water quality protection measures here. Geologic characterization is really key. And I'm just kind of, as a geologist, we like to say, you got to listen to the geologists. But you really need to get in there and understand the geology because, that's what the engineers are going to base their information on, how to construct and seal that well. And so you need, the engineers and geologists kind of have this funny little rivalry, but we need to work together and make sure that we, come to a consensus as to how to make sure the wells are constructed, protect groundwater or surface waters for that matter. There's a lot of tools in the toolbox. One of them would be running downhole geophysical logs, where you can begin to determine what is the bottom of fresh water, where do you start to see higher total dissolved solids concentrations in groundwater, are you hitting methane pockets along the way, and based on some of that information, how do you construct the well to make sure there are no water quality impacts. I'll say it one more time, conduct pre-drilling water quality testing surveys. If you do find elevated levels of methane in groundwater, there are a lot of analytical tools to be able to assess if in fact it is a thermogenic source, if it's geological methane, and in some cases you can even begin to figure out what formation that gas may have originated from based on its isotopic composition, and then be able to go back in and do some remedial work to seal that off if in fact that is an issue. And really, one of the most probably the riskiest aspects of this is all the fluids handling at the surface. So you need to make sure that the people handling all these fluids, whether it's the fracturing chemicals or the produced fluids, are trained, and make sure the best available engineering technologies are being used. So if there is a spill, which will occur inevitably, that it's either held within secondary containment, or there's liners so it can't seep into the ground, so it can be easily contained and cleaned up. And this just shows some examples of some of those technologies that are being deployed in the field. Again, lined well pads. This would be another close-up of a lined well pad. This is as it's being constructed. We're seeing more and more use of steel tanks be used out there, which minimizes the potential for spills and secondary containment. So if there is something dripping out of this tank, it doesn't leach out into the environment. And I thank you very much.